Hello everyone. I'll be talking about Swift, super fast and robust privacy preserving machine learning. This is a joint work with Mahak Pancholi, Arpita Patra and Ajith Suresh. This work has been published at Usenix Security Symposium 2021. The outline of my talk is as follows. I'll begin with machine learning in the outsourced computation setting, and then motivate the need for privacy preserving machine learning. I'll then talk about secure multi-party computation, MPC in short, and explain how PPML can be achieved via MPC. I'll then talk about the desirable properties of PPML via MPC and our results. Finally, I'll conclude with the future work. Machine learning is becoming ubiquitous. You can see it everywhere, beginning from transportation systems, recommendation systems, healthcare, to finance. So much so that solutions are being provided in the outsourced computation setting. For example, for the case of machine learning inference, let's say we have Alice who owns a model, a machine learning model, and Bob who is a client and wishes to run a query of its choice on the model owned by Alice. Assuming that they do not have the sufficient compute resources, they can outsource the computation and hire a server for the same. Here, Alice sends its model parameters to the server, whereas Bob sends its query to the server. The server performs the required machine learning computation task and sends the query or the output of the computation, which is the inference result, back to Bob. A similar setting holds true for machine learning training as well, wherein the data owners can send the training data to the hired server, which performs the required computation to train a model and sends back the trained model back to the data owners. It is known that more training data generates a more accurate machine learning model, and thus multiple organizations can collaboratively train a model by sending their training data to the hired server. However, there are privacy issues that arise in doing so. One of them is that the server that's hired to perform the computation can see all of the data on Clear. Another issue with the same is that, let's say, one among Alice and Bob is corrupt. In this case, let's assume that Alice is corrupt. It can collude with the server and thereby learn all of the training data that the other data owner provided as input. And this can be disastrous in some applications which deal with highly sensitive data. For example, in banking, where machine learning is used for fraud detection, the training involves developing risk profiles for banking customers. And the input that may be used for training a model may consist of transaction behavior of the customers. Now, this can be highly sensitive information, and leaking such information will not be something that banks would be ready to do so. And thus, this requires us to design privacy-preserving solutions for the same, wherein the required machine learning computation can be performed on the data, where the entity performing the computation has no idea about what is the input and what will be the generated output. Although paradoxical, such a privacy-preserving machine learning computation can be performed via the technique of secure multi-party computation, or MPC in short. MPC enables a set of parties with private inputs to compute a joint function of their inputs. And in doing so, it ensures correctness. That is, parties should learn the correct function output at the end of the computation, and privacy. Nothing beyond the function output should be leaked. Let us understand this with an example. Let's say we have 4 parties with their private inputs A, B, C, D. While they do not want to leak what their input is to each other, they are still interested in knowing what is the sum of all their inputs. MPC allows you to do so. Further, in the real world, some parties may be corrupt and behave maliciously. They may try to learn more information or try to deviate from the protocol execution. Such malicious behavior is captured by the notion of an adversary, and MPC guarantees security even in the presence of such adversarial behavior. The adversary can be classified into two types, semi-honest and malicious, where a semi-honest adversary follows the protocol but always tries to learn more information, whereas a malicious adversary may arbitrarily deviate from the protocol execution, so much so that it may even abort the computation, thereby resulting in denial of service. Now, depending on the misbehavior of a malicious adversary, various security guarantees are provided by an MPC protocol. The weakest amongst them is security with abort. That is, in an MPC protocol that provides security with abort, it allows a malicious adversary to misbehave such that it learns the output Y of the computation. But now the adversary can choose which other honest participants learn the output and which others do not. A slightly stronger notion is that of fairness, wherein either all the participants learn the output of the computation or none of them do. Thus, the protocol is fair and does not give any extra advantage to the adversary. However, observe that in both these security notions, the adversary can always abort the computation. Finally, we have the strongest security of robustness or guaranteed output delivery, wherein no matter how the adversary behaves, the protocol guarantees that the output of the computation will be learned by all the parties. And in this work, we focus on designing MPC protocols that are secure against malicious adversaries and provide the strongest security guarantee of robustness or guaranteed output delivery. As I mentioned earlier, machine learning in the outsourced computation setting involves hiring a server wherein Alice and Bob send its inputs to the server and the server performs the computation and sends back the result to the required participants. To perform privacy-preserving machine learning, we replace the single server which performs the computation by a set of parties or a set of servers which now run an MPC protocol to carry out the computation. Furthermore, the model parameter and query, which are the inputs of the model owner and client, are not sent on clear to any of these servers. Instead, they will be secret shared amongst these servers such that no single server will have any information about what the input is. Towards this, our contributions are as follows. We designed a robust PPML framework in the 3-server and 4-server setting with honest majority and malicious security. That is, at most one server amongst the 3 and 4 servers can be corrupt. We are the first to design a robust framework in the 3-server setting. Furthermore, it's not sufficient to simply design MPC protocols and assume that that is sufficient to achieve PPML. A range of primitives have to be designed, and towards this, several primitives such as multiplication, dot product, truncation, comparison, nonlinear activation functions, which are used in ML algorithms, are designed. Furthermore, as I mentioned, to perform computations in the outsourced computation setting and enable the clients to share their inputs among the servers, we design secure protocols for input sharing and output reconstruction. At the heart of our constructions lies a new joint message passing primitive, which enables attaining robustness without hampering the efficiency of our protocols. Compared to the existing 3-server setting, as provided by the work of Blaze, which is only fair, we perform as good as them with minimum overhead in communication while improving the security guarantee to robustness. With respect to the 4-server setting, and in comparison to the robust framework of Flash, we achieve a 2 times improvement in communication. Coming to the experimental results, we benchmark the training and inference phases of logistic regression, wherein for 3PC and 4PC, which is the 3-server and 4-server setting, we observe that we are on par or we have a slight overhead with respect to the existing framework. But note that the existing framework only provided security with fairness, whereas in the 4-server setting, we see a 2 times improvement. Similarly, for neural network inference, we benchmark 3 different neural networks and observe that in the 3-server setting, we are almost on par with that of the FAIR framework of Blaze. whereas in the 4-server setting, we observe a 2 times improvement compared to the existing 4-server framework. To conclude, we design a robust MPC framework for PPML in the 3-server and 4-server setting with 1 malicious corruption. And we benchmark PPML algorithms such as logistic regression and the inference phase of neural networks. Moving to the future work, as I mentioned, we design some building blocks. However, if we wish to do other machine learning algorithms such as decision trees, support vector machines, LSTMs, some other building blocks such as kernel functions have to be realized in a secure way. Furthermore, while our work considered fixed point arithmetic as the number representation, other number representations such as the poset arithmetic can also be explored. Thank you.